Let's start by summarizing something you already know. You know that Zn, the ring of integers mod n under addition and multiplication mod n, is a field if and only if n is prime. This is a field if and only if n is prime. So we know that means, one thing that means is that there are fields that have prime order. It turns out in finite field theory, there are fields that have non-prime order, but those other fields still have to have order equal to a power of a prime. One of the fundamental theorems of chapter 21 on finite fields is for each prime p and each positive integer n, there is, up to isomorphism, a unique field of order p to the n power. And we even give it a name and a symbol. We call it the Galois field of order p to the n. GF stands for Galois field, spelled Galois like this, G-A-L-O-I-S, do not say Galois. Galois field of order p to the n. And in fact, you can say more than this, but I'm not going to write it down. You could say any finite field must be a Galois field. It's saying a little bit more than what this is saying. This is saying for each, again, for each prime p and each positive integer n, there is, up to isomorphism, a unique field of that order, with that many elements, including 0. But you can also say more. Any finite field must be a Galois field. It must be of order p to the n. You cannot have a field of order 6, for example, 2 times 3, or order 10, 2 times 5, or order 15, 3 times 5. The order has to be a power of a prime. Okay? So let's start simple and try to construct some small finite fields. Start with the simplest that we really already know, Z2. It's just got 2 elements, and that in fact is the smallest field. We were wondering about this last week. There is no such thing as a trivial field. The 0 element by itself, effectively by definition, is not a field. In a sense, 0 by itself does act like its own unity, but remember the definition of a field is that it's a commutative ring with unity in which every non-zero element is a unit. But 0 by itself doesn't have any non-zero elements. So effectively, by default, it can't be a field by itself. Z2 is the smallest field. 2 elements. What's the addition table? Well, we've known that since group theory. The Cayley table as a group under addition is that addition mod 2. What's the multiplication table? Remember, fields are never groups under multiplication. So when I make a multiplication table for this, it's not a Cayley table in the sense of group theory. It's just a multiplication table. And 0 is the 0 element, so 0 times anything is 0. And yes, 1 times 1 mod 2 is 1. You could say the set of units in Z2, Z2 star, just as has the 1 element 1, that is a trivial group under multiplication. You could make its multiplication table very simply 1, 1, 1. Yes, that is a trivial group. You can have trivial groups, but you can't have trivial fields. So that's the smallest field there is. The second smallest is Z3. I'm not going to write that one down because what I'm more interested in today is getting to fields that have order equal to a power of a prime where the power is bigger than 1. What's the smallest such field? Not Z4, because Z4 is not a field. 4 is not prime. But there is a field of order 4 we would call it GF4, GF2 squared. But its elements would not be 0, 1, 2, and 3. I mean, at least not in the usual sense of those meaning, the meaning of those numbers under addition and multiplication mod 4. Because that would be Z4, and that's not a field. So it's got to be something else. So the question is, how do you construct a field of order 4? I hope from what we've been doing recently, if any ideas are going to come in your mind, it's going to be like, well, I guess we have to like maybe construct a factor ring by modding by a maximal ideal based on an irreducible polynomial. That's what we've been talking about. But what's the degree of that polynomial going to be? And what are the coefficients going to be? Better be kind of like as small as possible. The coefficients better be from Z2, and the representatives of the cosets better be like linear, right, with 2 coefficients, so that we have 2 times 2, 4 possibilities. And yeah, that is a way we could construct this field. Take the polynomial ring Z2x. So the coefficients are from Z2, and you do coefficient simplification mod 2. And mod by a maximal ideal, where the polynomial that generates that maximal ideal, that will also be a principal ideal, is an irreducible quadratic over Z2. So it's got to have an x squared in there. What else would be in there? You could try x squared plus 1. That would be the simplest thing to try. That doesn't quite work in Z2 because x squared plus 1 has a root in Z2, 1. 1 squared plus 1 would be 2. Mod 2 is 0. So the only thing really left to try is x squared plus x plus 1. I mean, you could try x squared plus x as well, but that doesn't work because it's got 0 as a root. Does x squared plus x plus 1 have a root in Z2? No, it doesn't. Try it. 0 squared plus 0 plus 1 is 1, not 0. 1 squared plus 1 is 3. Mod 2 is 1, not 0. So that's a quadratic that's irreducible over Z2. It's got degree 2. Remember, you can always just check the zeros if it's got degree 2 or 3. If it's degree 4 or higher, then it's harder, because that's where you have to worry about, could it have quadratic factors and that kind of thing. But we like the case where it's degree 2 or 3, because then we can just check for zeros. So it doesn't have any zeros in Z2, so it's irreducible over Z2. Therefore, we know from some theorems that this ideal is maximal in this polynomial ring, and therefore this factor ring is in fact a field. And we've also seen that the elements in these kinds of situations are cosets where the representatives can be written with a degree. You remember this? 1 less than whatever the degree of this thing is. I'll remind you why here in a second. We could write the elements as linear polynomial representatives, ax plus b plus the ideal. I'll go ahead and give the ideal name. I'll call it capital I just for short here. Plus capital I, where a and b are elements from Z2. And so you got 2 choices for a, 2 choices for b, altogether giving you 2 squared or 4 elements. 2 squared equals 4 elements. And it is a field. This has got to be one way to represent GF4. It's not the only way. In fact, I'm going to show you another way. And what I'm getting at with not the only way is you can write these things in more abstract ways. Let's go ahead and think about this particular field in a couple ways. Let's think about it this way as I've written it so far. And let's also be a bit more abstract with it to emphasize that we can be more abstract in how we think about these things. So if I do think of it this way, as a collection of cosets from a factor ring, which does happen to be a field here. Well, how would you write the elements? A and B could both be 0, so there's the trivial coset, I itself. A could be 1 and B could be 0, so we could also consider x plus I. A could be 0 and B could be 1, so we could consider 1 plus I, which maybe I should have written in the second spot because that's the unity. And the last element is going to be x plus 1 plus I. Let's go ahead and make quick addition and multiplication tables for this. So making the addition table. Oops, let's rewrite it. Let's put 1 here. X plus I, x plus 1 plus I. 1 plus I, x plus I, and x plus 1 plus I. As quick as we can, let's go ahead and add here. It will be a group under addition, right? Fields are always groups under addition. In fact, a group of 4 elements, we know from the fundamental theorem of finite abelian groups, will be an abelian group with 4 elements. It's got to be isomorphic to either Z4, it's either got to be cyclic, or the external direct product of Z2 with itself. Which one is it? Do your additions here. I plus itself is I. In fact, I is the 0 element. It's the same as 0 plus I. Add I to anything, I'm doing addition. I'm going to get that anything. Why? Because you add cosets by adding representatives. The representative there for I is effectively 0. I'm not writing it, but you can imagine it to be there. You can think of it as 0 plus I. So you add cosets by adding their representatives. What about this one? 1 plus I plus 1 plus I. Do a side calculation here. 1 plus I plus 1 plus I. Well, you could say that's 2 plus I, but in Z2, 2 is the same as 0. That's I. 1 plus I plus x plus I, that would be x plus 1 plus I. 1 plus I plus x plus 1 plus I, think about it with me here. The 1s are going to cancel effectively, right? Because 1 plus 1 is 0 mod 2. You're going to get x plus I. You'll get the same kind of things here. It's abelian. Getting close. What about the next spots here? X plus I plus x plus I. X plus I plus x plus I. You could say that's 2x plus I, but you mod coefficients by 2. That's the same as 0 plus I. X plus I plus x plus 1 plus I. The 2x would become a 0, but you'd be left with the 1. That's 1 plus I. And finally here, x plus 1 plus I plus itself. Let's see, this should be an I, not a T. Once again, modding coefficients by 2, you get 0 plus I, just I itself. What is this isomorphic to as a group under addition? Look at the main diagonal here. It's the identity elements under addition, the 0. I, the 0 element, as a group under addition, has order 1. All the other ones have order 2. They're their own additive inverses. This is not cyclic. It's isomorphic to the external direct product of Z2 with itself. What about as a group under multiplication when you look at the non-zero elements? So GF for star, what are the non-zero elements? 1 plus I, x plus I, and x plus 1 plus I are the non-zero elements. What's the multiplication table for that? 1 plus I, x plus I, x plus 1 plus I, 1 plus I, x plus I, x plus 1 plus I. It is a group under multiplication, the non-zero elements. Not all of the elements 0 doesn't have a multiplicative inverse. It's a group of order 3. It's got to be isomorphic to Z3. Because we know the only group of order 3 is Z3 up to isomorphism. It's got to be cyclic, actually. What's a generator? Well, let's see. Is 1 plus I possibly a generator? No, it's not, because it's the identity. It's the E. 1 plus I times anything is that anything. So I can quickly fill in this part. 1 plus I is the identity under multiplication of GF4 star, meaning take the Galois field of order 4 and take away 0. That's what the star means. Is X plus I possibly a generator? Well, if you think about what you know from group theory, Z3 itself has 3 elements, 0, 1, and 2. Both 1 and 2 are elements, are generators. Both of these 2 elements have to be generators, in fact. What's X plus I times itself? It's got to be X plus 1 plus I, though it doesn't look like it would be, would it? Does it? X plus I times itself. You multiply cosets by multiplying their representatives, you get X squared plus I. And now this is getting at Anna's question. How do I know I can write elements as linear polynomials in front of the I? Right, that was your question? Because you can always simplify these things using the fact that that's the ideal. Because our ideal I, another side calculation over here, is the one generated by X squared plus X plus 1. That means anytime I have, well, it means this, if I have X squared plus X plus 1 plus I, that X squared plus X plus 1 gets sucked into the ideal. It's the same as the trivial ideal, the 0. And that's equivalent, if you subtract X and 1 from both sides, to X squared plus I being negative X minus 1 plus I, but the coefficients are modded by 2. That's the same as X plus 1 plus I. Mod 2. Because of that, the equality there, that means we can simplify this to X plus 1 plus I. And that means that's what goes right here. As it has to be. We knew that ahead of time. It had to be that because we know these non-unity elements have to both be generators of the cyclic group of order 3. So when I square this element, it's got to be the other non-identity element. If I multiply it times X plus 1 plus I, we know ahead of time it's got to be the identity element. These two things have to be multiplicative inverses. Check it. X plus I times X plus 1 plus I. Multiply cosets by multiplying their representatives, you get X squared plus X plus I. But then X squared plus the X squared here can be replaced by X plus 1, just like it was in the previous line. So this becomes 2X plus 1 plus I. But then we can mod by 2. This is the same as 1 plus I. Mod 2. Mod the coefficient of X by 2 to get 0. We've got to get 1 plus I right here. In a similar way, we got to get 1 plus I right here. What about what goes there? If you think about it, without even doing a calculation, it's got to again be the other non-identity element. It's got to be X plus I. Let's check that one. If I take X plus 1 plus I and multiply it times itself, by foiling the representatives here, X plus 1 times itself is X squared plus 2X plus 1. But then 2X is 0 because I mod that coefficient by 2. X squared gets replaced with X plus 1. just like it did up here and up here. So this becomes x plus 2 plus I, but then that 2 becomes a 0 because I mod by 2. This is just x plus I. Once again, mod 2. And therefore, I knew what the answer was going to be. It is indeed x plus I that goes there, the other non-identity element. So as a group under multiplication, the non-zero elements of GF4 is isomorphic to Z3, cyclic. As a group under addition, all the elements of GF4 was not a cyclic group. This is a special case of a more general fact. The structure of finite fields as a group under addition, GF p to the n is isomorphic to, well, it's not a cyclic group. It's an external direct product of ZP with itself with n factors, meaning there's n of these, n being the power of p. And as a group under multiplication, the set of non-zero elements of GF p to the n, meaning GF p to the n star, is cyclic. It's isomorphic to Z sub p to the n minus 1. Why minus 1? Because we took away 0. Mentioned 15 minutes ago, we can also think of this GF4 more abstractly. This is a fairly concrete representation of it, you might say. We could also think of it more abstractly. How? What am I getting at? Well, we could just shorten our symbolism effectively. We could, for example, give that element a shortened name. Maybe call it omega or something like that. We could still be referring to the same field that we constructed, this one, but just shorten our notation, call that omega. If we do that, it's also going to be convenient to use shorthand, say, for the 0 and the 1. Effectively use the symbol for the number 0 to represent the coset 0 plus I, which is just I. Effectively use just a plain old number 1 for the unity coset, 1 plus I. Omega is x plus I. What would be the other coset? X plus 1 plus I. How about omega plus 1? Effectively, just shorthand notation is what these equal signs mean. Shorthand notation. I'm defining these symbols in this way. With that shorthand notation, I can reproduce the Cayley table for the field under addition and the Cayley table for the non-zero elements under multiplication using just these shorthand symbols. So for example, the addition table would be 0, 1, omega, and omega plus 1. And go ahead and add where coefficients get modded by 2. Do as quick as I can here. 0 still acts like the additive identity. So I can quickly fill in those. 1 plus 1 is 0 mod 2. 1 plus omega is omega plus 1. 1 plus omega plus 1 is omega, because 1 plus 1 is 2 is 0 mod 2. I can very quickly fill in this table. And I'm really not doing too much different than what I did before. The only thing I'm doing differently is I'm just using the shorthand notation for these coset elements. Omega plus itself is 0 because it's 2 omega mod by 2. Omega plus 1 is 1. Omega plus 1 plus itself is 0. This is effectively the same Cayley table as this was. Just a lot quicker to write. Now, again, I'm defining these symbols in this way, but you know what? Just as in group theory, I could think about fields in a purely abstract way. Once I create this addition table and the corresponding multiplication table as I'm about to, I don't have to think about the factor ring at all anymore. I could just say, hey, there's my field of order 4, my Galois field of order 4. and think of it just in a purely abstract way, and that's often good enough. So for the multiplication table, make that quick too. 1 omega and omega plus 1 are the three elements. 1 is the unity. It's the identity for this group under addition. What's omega squared? Omega squared is omega plus 1. Why? Because x plus I squared was x plus 1 plus I. That's why. I am, again, in my mind, relating this back to the more concrete example where we're actually representing the elements as cosets. But I could think of this abstractly and just effectively define omega squared to be omega plus 1. And omega times omega plus 1 is omega squared plus omega, but omega squared can get replaced with omega plus 1. Mod the coefficients by 2 and get 1. That's a 1. Omega and omega plus 1 are multiplicative inverses. Likewise, it's abelian, so this is a 1. What's omega plus 1 times itself? This is going to be a group under this multiplication. It's got to be whatever is left over here. It's got to be omega. Is omega plus 1 times itself equal to omega? Multiply it out. Mod coefficients by 2. Replace omega squared with omega plus 1. Mod coefficients by 2. Get omega, just like I said. I went by kind of fast. You got to check these calculations on your own, maybe after class. Double check it. You can do it. Okay. The key equation is this one right here that I'm using to simplify, plus modding coefficients by 2.